All right. So, full disclosure, recording has begun. With that being said, let's look over onto the back side of that sheet. The only problem that we did on the back side of the sheet, or that we didn't do on the back side of the sheet, is number 8. And number 8 deals with a space station. Always a good way to start Friday. So, all right. Number 8 says a space station is designed to be used as a space colony. So futuristic. The engineers want the inhabitants to experience a centripetal acceleration equal to the acceleration of gravity here on Earth. The space station has a diameter of 8 kilometers. Part A says, what must be the tangential speed of the outer edge of the space station to achieve this centripetal acceleration? We talked earlier in the week about the idea of centripetal acceleration and centripetal force. First, an object moving in a circle. Is it accelerating? Yes, because it keeps changing directions. And that acceleration is directed how? Where does it point? Inward, toward the middle. Always perpendicular to the way that the object or that object is currently going. So we say that the velocity and the acceleration are perpendicular. We said that if you have inertia telling you to go one way and a force telling you to go another way, you're going to go somewhere in the middle of that. Okay? And that acceleration needs to be caused by a force. For part A, we talked about the centripetal acceleration of an object is determined by its tangential speed. Tangential. There's no extra I in there. And the radius of that object. So in this case here, it says we're looking for a tangential speed, right? It says what must be the tangential speed of the outer edge of the space station to achieve the centripetal acceleration. So it said they want the centripetal acceleration to be equal to the acceleration of gravity, which I hope by now you're familiar with, right? So what are we going to plug into this equation here for centripetal acceleration? Okay, so this is going to go 9.81 because we want that centripetal acceleration to be equal to the acceleration of gravity. We're solving for the tangential speed, and it told us something about the space station. It told us that the space station has a diameter of 8 kilometers, but we don't need that in this problem, right? What do we need? Radius, okay? However, 9.81 is in which unit? Meters per second squared, but this 4 is in what unit? Kilometers. So we can't have that. So we got a couple of options. It's probably easier if we turn this radius into meters. So now we've got what we need to do what we need to do. So go ahead and solve for the tangential speed of this space station. Good job, JG. So did we get somewhere around here? Yeah. And then if we're going to sig dig that. Okay. So, in order for that space station to experience an acceleration equal to our acceleration here on Earth, it has to spin at 198 meters per second, which is pretty fast. Yeah, exactly. B, how long will it take the space station to complete one rotation? So we talked about that tangential speed is a meters per second number. And in your lab on Wednesday, you calculated the tangential speed of that object by doing what? Does anybody remember? Yeah. You took the circumference of that of the circle and divided it by something that we refer to as the period, which is a time, but a time specifically for what? One rotation. So if we plug this stuff into here, can we figure out how long it would take the space station to rotate once? Do we know the tangential speed? We do. We know the radius, so we should be able to figure out the time. Okay. Why don't we do that now? Make sure you do your algebra correctly, right? Variable in the bottom. Don't get tripped up there.
Question. On this lab, I don't know. I remember you told me like how to find it, but I don't know how I found it again.
We're doing that right now.
Yeah, but that's what I did.
Do you know the radius for the circle?
Yeah.
Do you know the time it takes to go once around?
Yeah.
Then you can figure out the.
I don't know.
Did we get an answer here yet?
Yes.
What did we get? What? 126.9 seconds? Is that good? Okay. Probably sig dig wise, we'd go 127. But alright. Let's skip number 3 right now. Or sorry, letter C. And let's go right to letter D. We could, but you need a little bit of information. I really want to get to know that kind of problem that we're going to do today, so let's not worry about that. It's just exactly the same as this, but we have to figure out some of those numbers first. So, yes, Billy?
How would you spin a spaceship in space?
You have to start it spinning, okay?
Yeah.
But once it starts spinning, what will it do?
Well,
There's no, well, not that there's no gravity, there's no what? There's no air resistance or friction.
if you get like one engine just spinning around once,
Yeah.
they won't the spaceship will fly into.
If you orient it the right way, this gets into like torque, which we haven't really talked about just yet. So because it's an object, if you apply a force to an object not at what we refer to as its center of gravity, for a circle, the center of gravity is going to be where? Right in the middle. So if you apply a force that's not right through the middle, you'll cause it to start spinning. All right, and we refer to that as torque, and we're probably not going to get to that this year.
I'll come back next year.
Yeah, you want to, so.
Hey, senior.
I'll write you an email and say, hey, Billy, tomorrow we're going to talk about torque. So anyway, but then the important part being though, once you get it to start spinning at a certain rate, because of the lack of friction, the lack of resistance, it'll just keep going, the whole inertia. All right. It takes 127 seconds for this space station to go completely around, right? Which I hope by this point in your life, whether you're a science person or not, you realize that that's why the sun rises and sets, right? Because we spin around in a circle. What? I know.
I thought the sun revolved around us.
Yeah, exactly. So yeah, I hope. Yeah. I know. I see. These are things they don't tell you, and that's why we try to keep you interested all the way till the end of senior year, by revealing these things to you. I know. But
I'm so glad this is recorded.
I know.
I always get so
So,
Oh, I forgot about that.
yeah, I didn't. Don't worry. What?
It's too bad we didn't record Wednesday.
I know. All right. For D, it says how many times will the sun? Ooh.
Oh, sorry.
I've been sick all week. Great.
Well, I always catch
and I
it.
played 2 soccer games in the last 2 nights. My voice is a little shot right now. So. All right, how many times will the sun rise? How many times will the sun rise and set on the space station in one 24-hour Earth day? So we know that the sun will rise and set once every 127 seconds on the space station, because that's how long it takes it to spin. So in order for us to figure this answer for D out, what are we going to have to know?
Convert it to hours.
How many seconds are in a day? Or we could convert this into hours and do it that way. So
How do you sleep?
pretty much.
So,
So
get 2 minutes of sun.
That's cool. Yeah.
if we figure out,
blind.
we know that there are 60 seconds in 1 minute, right? 60 minutes in an hour. A little less than 24 hours in one day, but we'll go with 24
Little.
hours just because not, then it
Then a
takes.
little bit.
What is that actually?
What is that?
A little less than kind of.
little less
20
than kind,
It's
yeah.
23 minutes, 50 or 23 hours, 56 minutes, 4 seconds. It actually takes us to rotate. So. And when you do all that, you end up with, if I'm not mistaken, 86,400 seconds.
Yes.
Right?
Impressive.
Sad that I know that, but that's my life right now. And
Your life is awesome.
you know, yes.
Physics.
You know, I can motivate students so well. It's like my life. So, but if we take 86,400, I know.
Oh, man.
And it's being recorded too. Yippee.
You guys can all go home and watch it.
Yeah, I'm sure all of you will go home and watch it. I'm sure.
That was this big
That'll
became like a viral video. And you
Yeah.
like,
Wait, Nate, it's okay.
Anybody got a calculator handy here? And they can run this through real quick and give me an answer.
680.
So, in this case, and it's only first period.
Holy!
So,
Crazy.
in this case, with the space station rotating once approximately every 2 minutes, this many seconds in a day, if you're one of those people who like sunsets and sunrises, you got 680 of them every day. So,
There's only like one Earth day.
one Earth day, yes. So, you know, I'm assuming that on the space station we'll still like set the clocks to, you know, what Earth is like. You know. But anyway.
It depends like where you're from.
That doesn't actually.
Well, I
that
mean,
doesn't
that's true, but they could pick one time. Probably Greenwich Mean Time, I don't know.
That's not the like.
Well, wouldn't
This
matter
is the
what
real
time
space
you're at.
station.
If you're at
No, yeah, this isn't the real, no, this isn't the International Space Station. So. Alright,
things legit.
from that point, let's go here to the new problem set that I gave you today. What we want to do, or what I want to do, over the next week, is take a look at mathematically analyzing this idea of centripetal force and see how it contributes or what's required in order to produce this circular motion. So up at the top, it says that, as discussed earlier, the force that maintains circular motion is not a new kind of force. We used, either successfully or unsuccessfully, depending on how you want to look at it, the whole James Bond analogy that centripetal force is like a role that needs to be played, and something has to fill that role. So any of the forces that we've previously discussed in class, and some forces that we haven't previously discussed, can be used to maintain circular motion. So it can be friction, it can be tension, it can be gravity. Any one of these forces can act as centripetal force as long as it's acting correctly on that object that's moving in a circle. But regardless of how we go about doing it, we talked about that centripetal force the amount of centripetal force required is equal to mv squared over r, where m is the mass of the object moving in a circle, v is the tangential speed, r is the radius of that circle. If we take a look in the first section here, friction number 1. You'll notice on that sheet there are a couple different sections. We'll do a couple of problems from each section every day this week. So I know there's not a lot of room on there to write, but I wanted to get it all on one page. So it says, a car with a mass of 1,234 kilograms approaches a flat curve on dry pavement that has a radius of 45 meters. It says, what is the maximum tangential speed that a car could travel around the curve without sliding if the coefficient of static friction is 1.20? So we start at the beginning. What is this question actually asking us for? It's asking us for tangential speed, right? What is the maximum tangential speed? V equals question mark. Things we know. Okay? They give us the mass of the car. 1,234 kilograms. They gave us the radius of the curve being 45.0 meters. And then they give us a coefficient of static friction equal to 1.20. In this case, it's probably a good idea for us to draw a picture to sort of help us out with what we're doing here, okay? The picture can be, not what I wanted to do. The picture can be a little confusing. So, I am going to draw you a picture of a car coming out towards you.
This should be interesting.
I know, yeah.
Yeah.
Woohoo. So, we'll go red car, okay? All of my cars are Volkswagen Beetles, by the way. Just give it some headlights.
Yeah, headlights.
Here.
There you go.
Here. Maybe
Looks
like
like
a radiator grill here.
You get an antenna. That's like a beatbox. I want to see an antenna.
Looks like a radio.
Yeah.
So,
They get a little horror.
some side view mirrors.
I like it.
You know.
Oh my gosh, look at that.
So does it need it? Does it need an antenna? So
Looks
there.
evil.
Oh, yeah, now you take it too far. Looks like
Yeah, that was too much. Okay. So, are we good with my car that's coming out towards you? Okay.
Yeah, that's one of your better drawings.
So I practiced this one. So
I don't think the mirrors are in the right place.
yeah, probably not, but I mean, okay.
I like how there's like a box with like
So this car is going to be coming out the board, or coming out of the board at you, but it's going to be making a right-hand turn. Okay? So it's going to be turning this way. If we look at forces that are acting on this car right now, there's 3 of them. What's the first one that we can start with? Okay? Gravity's still got to be there. Regardless of the fact that this object is turning, still has to be a gravitational force. Okay? There has to be a normal force in this case, because the acceleration is a left and right acceleration. Right? It's going around the curve towards your guys' left, towards my right. What would that mean about green and blue in this case?
Cancel out.
Is there any up and down acceleration? There isn't. Then there has to be one more force. If this object is making a right-hand turn, or the way you guys are sitting, it would be towards your left, right? What else does there have to be here? There has to be a centripetal force. Where is the center of this circle? Pretty much where I'm standing, right? Okay. Which means there has to be a centripetal force that looks like this. Does that make sense? So we'll label this as F of C for centripetal force. We'll label this as F of N. We'll label this as F of G. Conceptually, we just talked about a couple of things. First, hope by now we know how to calculate this, right? So let's do that real quick. Let's find out the force of gravity.
1, 2, 3, 4.
Is that what it is, Lord?
Yeah.
Okay.
Point
That'll be good. We'll leave it like that. And then we talked about conceptually, that also means what has to be true about normal force. That has to be the same as well. Okay. This has to be 1,200, 105, or 12,105.
Yes.
Here's where this problem becomes different than the problems that we've done. We talked on Monday that centripetal force is not some new kind of force. Something has to go here. In this problem, what's preventing the car from going in a straight line and making it go into this curved path? Well, you turning the wheels, but what does that do on the surface? It creates friction on the surface. And friction prevents your car from going in a straight line and makes it go into that curved path. That means here, there is a centripetal force, but what's providing that centripetal force? Friction. So here, we could label this as centripetal force, but we could also label it as static friction. It's a static friction force, kind of in a complex way, but don't worry about that right now. Okay? Does that make sense on the picture? Yes, no, maybe. So here's where all of these problems have to start. All of these problems in this chapter start like this. F of C equals. And then it's a matter of, well, where does centripetal force come from? We just established what does centripetal force have to be equal to in this case? Static friction. So that's how this problem starts. On the left-hand side, centripetal force. I've given you a formula to calculate how much centripetal force this object needs, right? What is the amount of centripetal force an object needs to make a turn depend on? Depends on three things. Depends on the mass of the object, its tangential velocity, and the radius of the turn. That together has to equal static friction. Do we have enough information now to solve for our tangential speed? Indirectly, yes. Do we know the mass of the object? Yes. Do we know the radius of the object? Do we know the force of static friction? Not yet, but we can find it. Right? They gave us, in the problem, the coefficient of static friction. We know that the coefficient of static friction is equal to the maximum static friction over the normal force. Can we use this to find the maximum static friction? We know the coefficient, we know the normal force, right? Okay. So we can find it. The problem says, what is the maximum tangential speed? So if we're looking for the maximum tangential speed, that means we're going to need the maximum static friction force. So let's plug numbers into the coefficient of friction equation, find out what our static friction force is. Once we figure that out, that's going to go over here, and now we can solve for the tangential speed. Actually, Jesse, once you like get the pattern, setting up the problem is actually pretty easy. Then it's just a matter of finding
I
that
don't
one.
like when things just equal other things, like how you can say like F of C equals F of S.
So that's part of the thing with the centripetal force. It's got to come from somewhere, right? It's got to be equal to something.
Yeah.
Anybody actually run it through their calculator? Or?
I got it right.
Yeah.
23?
First one of this thing.
Nice. Well done, everybody. Well done. All right. I'll set up problem number 2 and let you run through it. I know, it's generous of me, isn't it? Number 2 says, a flat curve on a highway has a radius of 240 meters. Car goes around that turn with a speed of 26. What is the minimum coefficient of friction that will prevent the car from sliding? That's how it starts. Oh, there's a reason why I didn't do this problem. It sucks. Not that it sucks. It's just a little harder for, you know.
Which means so. In other words, it sucks.
It's a little bit harder than, you know.
Wait. Pottery is zero. Pottery's at 8.
So,
Yeah, I got 3.
instead of number 1, or instead of number 2, number 6, okay? Number 6 is a problem very, very similar to problem number 1. Okay? Anybody ever been to the Indianapolis Motor Speedway before?
Have you?
Yes, I have.
Is it exciting?
It's all right.
I mean,
I used to live in Indianapolis when I was young, so.
what else could happen besides going in a circle?
Things can crash.
Yeah, that's what it
Does that happen every single time?
Yes.
Yeah.
There's always a crash. Oh, well then yeah, that's exciting.
And they go past you at like 220 miles per hour.
You like move?
That's scary.
What?
Like you know, like when cars go, like you're sitting inside your car and it goes really fast next to you, and you like your car shakes.
I don't know. It's been a long time since I've been there.
Like, all right, you know,
That
like
happens when we're turning.
typically, yeah, the car shake.
It's so scary. You're sitting there and like you're still passing
Yeah.
and it's like. And then 2 cars pass from both directions.
Yeah, and just like shake. Like, try and turn in and not
All right. So, for part A of this problem, there's the information that we have. From this point, it's exactly the same problem as number 1. Picture's the same. What you need to do to get there is the same. For B, the only thing that's different is the fact that you have a different mass for that object.
You will find the same.
It's pretty easy. Just to divide this number by 2.2 and you'll get it. Yeah. But everything else is set up exactly the same. Okay. Why don't we work on those 2? I'll give you back your tests. You can look at them. Okay. For this weekend, I do have take-home tests, or do have a take-home quiz for you. I'll give you that as well. And then there's a couple of problems on the calendar off of this sheet that are similar to what we did in class today. Okay? We'll come back on Monday and we'll start a different type of problem. I know.